Alright, so today I'm going to talk a bit about a commonly asked question in forums, and that's why do GPUs not have socketed memory, so we can add more memory if we want to do it later, and why can we do that on CPUs? And we'll look at also the corollary of this, which is why can GPUs have much faster data rates on the memory than CPUs. And so we'll look a little bit about the signal integrity and sort of how and why it's so challenging, and basically look at what are the difficulties when it comes to organizing a memory system like this. And the short answer to the question is really that having the memory on a card or anything that you can quickly remove, or the user can quickly remove without soldering it, is really difficult to manage in terms of the signal integrity. So why is this difficult to manage in terms of signal integrity? We'll get into the details later. But the first thing I want to go over is, of course, the operating frequencies and the data rates of these different systems. And here on the right I have the data rates laid out. So for DDR4 we'd be looking at, for JDEC, 2133 to 3200 mega transfers a second, and you might get 4000 plus maybe 5000 even if you have a really good motherboard and good memory chips. GDDR5 would be 8 gigabits per second, GDDR5X 11, GDDR6 with 14 for most of the implementations so far, but of course it's been validated up to 18. And I'm not going to touch on GDDR6 specifically here because it uses a different encoding system, but basically with all of these DDR4, GDDR5, GDDR6, apart from GDDR6X, these all use the same signaling scheme where when the clock goes from 0 to a 1, or from 0 to a 1, we can encode a piece of data. So we would stay at a 0 for one state, or we'd change the state on the what's called the clock edge to indicate a different state. So rather than saying a 1 or a 0, in the terms of the voltage representing a data bit, we represent the data bit in terms of the change from the 1 to a 0. So we can do that twice in every clock cycle. So that's why we have the double data rate thing, where the actual operating frequency is half of the data rate. So the data bus frequency for these is respectively about 1000 to 2000 megahertz for DDR4. It's 4 gigahertz for DDR5, 5.5 for GDDR5X, and this should be GDDR here. See, can we add a G? So GDDR5, 4000 megahertz, and then GDDR6 is one of the fastest, at least for memory that I know of, buses, and it operates at 7 to 9 gigahertz on the data bus. And so when we think of transferring data through a PCB or through any interface, through any signal line, we can use the same analogy we usually use for electronics, where we have where we look at it as a liquid or a fluid in a pipe. And in the case of transferring signaling data, we don't really want to push a liquid. We don't want the objective isn't to move liquid. It's not like we're trying to power something with the fluid in the pipe, but rather that we're going to change the pressure. So we're going to change the voltage on the line in some way that the receiver at the other end of the line can detect that change in voltage. So essentially what we're doing is we're transferring sound down the line, or the equivalent of sound. We're making waves in the line, pressure waves or voltage waves in the case of the electronic. In the case of electronics, it's of course the voltage waves, and those voltage waves are then picked up by the receiver, and that's how we get the data from point A to point B. So when we think of when we think of sound, we have to remember, of course, that sound, if we kept with this analogy of the pipe, we have to remember that the sound is going to reflect off the pipe. So if we have a curve in the pipe, we might see that the sound that the sound bounces back more than it continues down through the pipe. Or if we put a mirror or something, or some surface, not a mirror using sound, but if we put some reflector right in the corner at the right angle, we can get much better transmission of the sound continuing down the pipe. If we change the shape of the pipe as well, so we go from a narrow pipe to a wide pipe, or then back to a narrow pipe, we only we're going to have a problem that there's going to be this large surface that's going to reflect the noise signal, the waves, back in a different way. And the same happens in electronics when we're transferring signals through electricity, changes in voltage, through a copper wire, through any conductor really. And what's going to happen is if we have a change in the conductor, we change the width of the conductor, we change the material of the conductor, we change the shape of the conductor, that's going to cause some of the signal to be either absorbed, reflected, or something is going to happen like that. And we can also, of course, have the interaction with electromagnetic interaction with the line next to it. So we can create interference between two different lines by changing the voltage on one of the line. Usually you'd refer to them as as one of them would be a victim line, and I forget what the wording is that you use, but anyway, the point is there's a lot of ways we can generate interference on such a signal line. So really what we want to do with a signal line like this is, especially when we're operating at these very high frequencies that we have in GDDR, which are, these are frequencies, these are what, 6 times maybe higher than what we're using in DDR4. So suddenly we're much more sensitive. We have to change the voltage much more quickly. So it's much easier to have these reflections damage the data that's in our that's being transferred. And what will happen is we'll get just a background fuzz of noise that will overpower our ability to sense whether the signal is a 1 or a 0. It's been changing from 1 to a 0. So the objective, of course, is to minimize that noise, and one of the key ways to minimize that noise is making the signal path, so all of our conductors that take the signal from place 1 to from our sender to the receiver, as simple as possible, and have them be as uniform as possible, so the least possible change in the diameter, the cross section, the shape, and the material. And so in the case here, in the top case here, where we have the PCB here in green, we have the conductors, we have the wires within the PCB are, of course, are here in brown, and then we have the red. These are columns in the PCB, or vias, where we have a vertical connection. So say if we want to go to one of the deeper layers, we need to basically drill a hole. It's not actually done with a drill, but we drill a hole and insert a piece of metal in there, basically, so that we can get down to the lower layer. And so what we want to do here is, obviously I've ignored the fact that inside the silicon, or inside the package, there might be a lot of different things as well, but these will be the same regardless of whether we have whether we just put the memory chips on a PCB like we would do in a graphics card, or whether we put them on a memory module like we do it with DDR4. So we have challenges here that we need to overcome to maintain our signal integrity, because we're already transferring through different mediums. We have to transfer through these solder balls on the bottom of the package. We have to go through the via, then we have to go through the conductor. The conductor might not be straight either. There might be interference from adjacent conductors. We might have to put a ground fill above. You know, you might have seen this with a lot of recent motherboards, that they put a ground layer essentially above and below the memory traces, so that there's less interference between between different conductors, and that ground layer essentially shields it from other conductors that are moving through that area of the board. Commonly also, you'll see on some motherboards that the area where the memory traces are, there's nothing there other than the memory traces themselves and everything related to the memory. And again, that's to keep that area clear of the interference that would cause damage to our signal integrity. So we already see that it's already a complex system in terms of the signal line, and that there's already a lot of different interfaces that the signal has to go through. And now if we make that now into a memory module, now it's even more, because now we need to have the pins in our memory module. These will go through the board. So now we have a loose end of metal sticking off the back of the board where the pins of the memory module go through. The memory module has to have the pads, and the pads will have contacts in the slot that have to make contact with the pads on our module, and these contacts will not have they won't have optimal shapes because they have to be springs. It might be hard to get a perfect a good contact from one piece of metal to the other, because these are obviously, you have to be able to remove the memory module as well. So the shapes of these things are determined by the fact that we have to mechanically make the connector be able to be removed and inserted by the user, and we can't necessarily always focus entirely on just the signal integrity aspect. And we have two different PCBs as well. We have to have the vias in our motherboard as well. We have to have the vias in the memory module, and of course in the memory module we'll have two vias. I'll add another one here, right? Because we'll have to have the vias going from the contact pads as well. And as we see, the contact pads have to contact with, as I said before, the contacts in the pins in the slot. So the complexity of such a system is vastly increased, and then we have to account for the fact that one memory module might not have the same PCB, might not have the same characteristics as a next memory module. So now it becomes a massive problem of, well, we need to be able to support the different memory modules. One of them might have certain characteristics, one of them might have different characteristics. It might be impossible to match the characteristics along the length of the conductor well enough that we can reliably get a signal at the higher data rates we're trying to get with GDDR. And so this complexity in the conductor, and remember back to what I said about the sound, the different shapes, the different diameters of the conductors, the different materials in the conductors, because obviously these pins are going to have to be special materials so that they're springy enough to make good contact when you put the module in the slot. So all of these things make the signal integrity much harder to be maintained, and therefore it's not really viable to take a higher bandwidth, a higher frequency interface such as GDDR5 or GDDR6 and use modules in such a thing, because it's just way too complicated, and it might not even be possible. It's physically impossible to actually get good enough signal integrity while maintaining a low enough operating voltage, that we aren't, throwing away power. And we already see today that GDDR5 and GDDR6 are extremely power hungry interfaces, even when you have a good, simple memory trace layout. We still have massive power hogs for the memory transfer and GPUs. That, there's a reason we're trying to go to HBM, because it means that the signal integrity is much easier. We can have a wider interface, rather than having a faster conductor, we can have a wider conductor. So it's just a lot simpler at the end of the day to go to a lower speed. But obviously, when we need the high speeds of GDDR5, we need to have that simple, just package to package interface, without having to deal with the slots, without having to deal with potential differences between one module and the next. And so basically, it's just too difficult in terms of signal integrity, and that's the core reason for why we don't see modules for GDDR interfaces, and why I think there never will be. And actually, I wouldn't be surprised if in the future we see us moving away from memory modules the same way we have them now, because it's just very difficult to make good signal integrity when you have different interfaces like this. And so yeah, I hope you learned something in this video. If you have any comments or suggestions, put them down below, and I'll see you in the next one.